Let's look at another surface area. The parametric representation is very useful, and since they tend to repeat quite often, we can minimize our calculations if we just keep little tools in our hip pocket to use when we need. What we want to do is to compute the surface area of a dome. And if you look here, our parametric representation is that of a sphere. However, it's incomplete when we look at the region R, but we have 28 cosine B sine U, 28 sine B sine U, and 28 cosine U. Now, if you look here in the blue, this mimics the more generalized parametric representation of a sphere that we've used in the past. And so we don't have to repeat the calculation. As you see in your notes, the calculation is done for you. That is, when we take the norm of the surface normal, we get a squared sine u. So we see that this and this are basically the same, where a has been replaced with 28. And so that's really good. We have that computation ready to go. So now what we see here is we do have a dome, but it's a partial hemisphere as I've drawn here. Notice that the u does not descend to pi over 2 to give the complete hemisphere. And so we have the v running from 0 to 2 pi to give us the circle in the xy plane, or planes parallel to that, but this is only a partial hemisphere, so we have a dome like maybe an amphitheater or something. And so what we want to do is to compute the area of that. So our formulation for area is the double integral of the norm of the surface normal over the region R. But we have the norm of the surface normal if we simply replace a with 28. So in here we have 28 squared sine u du dv. That is where the v runs from 0 to 2 pi and the u runs from 0 to pi over 3. So we saw in the last calculation that we didn't have a parametric representation that was familiar to us, so we worked it out by hand. But this is a very familiar parametric representation, and so we can utilize that fact. And so now notice that the sine u bears no dependence on the v, so we can break this up. You can factor the 28 squared, which is 784, and we have the integral dv from 0 to 2 pi. And then, of course, we have the integral of sine u from 0 to pi over 3. So now, of course, the antiderivative of sine is the negative cosine. So I go ahead and factor the negative here. And of course, this integral with the dv, just gives us 2 pi. And of course, we evaluate the cosine from 0 to pi over 3. And so now, of course, the cosine of pi over 3 gives us a 1/2. And of course, with the fundamental theorem, the cosine of u when u is equal to 0 gives us 1. So we have the -1 here. This gives us a negative 1/2. And so these 2's absorb. And so we have a negative 784 times a negative pi, which gives us an area of 784 pi square units. So again, I want to make the comment here that we need to look for particular parametric representations that are familiar to us, because this can save us plenty of time. Just like being a physicist or a differential geometer or an engineer, you look for these patterns to save computational time. Very elegant example, and we are done.